Good morning. This video is on the normal force, and for some students it seems like such an insignificant force. It's always there. Why is it so important? Why does it have its own video? Well, the normal force is a very important factor that determines the amount of friction that an object experiences while either stationary or moving. And we know that friction is very important because in the engineering world and in the energy world, people selling energy, people selling engineering ideas, knowledge, components, appliances, apparatuses, whether it's static friction or kinetic friction, the amount of friction determines the amount of energy loss or energy transference. And we know that whenever an object loses unnecessary energy, that means unnecessary loss in money. And we know that money makes the world go round. So the normal force is extremely important because it has a great impact on the amount of frictional force, either kinetic or static, that an object experiences. So here are a few characteristics of the normal force and do's and don'ts when you're dealing with normal forces. So when you ask any questions about normal force, whether to draw them or calculate a normal force, please remember the following. Only objects on a surface, if the object is in contact with that surface, will experience a normal force. Any objects moving through air or hanging in the air or suspended in the air or moving through water or snow or mud, any medium where objects move through that medium, guys, those objects do not experience a normal force. So if you step on snow, your foot goes into the snow. So the upwards force of snow on your foot, that's not a normal force, because if you look at the third bullet, it's very important that you know that a normal force will always prevent the object from passing through the surface. And neither snow nor mud nor water or air do that. Objects can freely move through mud, through snow, through water, through air. But if you are on a tar road or on a wooden table, those surfaces will prevent the object from passing through the surface. So the bigger your normal force, the harder that surface must push upward away from the surface to prevent the object from passing, from falling through the surface. That is what the job or the work of a normal force is. So if you see an object sinking into a surface, then there's no normal force present, because a normal force is a measure of how hard the surface must push or work in order to keep that object from falling or pass into the surface. When we draw the normal force, please remember that a normal force must always be perpendicular to the surface. Now, when you work with a horizontal surface, it's very easy, normal force just straight upwards. But if we are moving on to inclined planes, when you are working on a slope, then that can get very tricky. So please remember, if you work on a slope, then your normal force must be perpendicular even to your slope. So that angle must be a 90-degree angle. And then that is then my normal force, perpendicular to the surface. The next bullet, also very important, because this bullet tells us what determines the magnitude of the normal force. The direction of the normal force, always very easy. It's perpendicular to the surface, upwards, away from the surface. The magnitude of the normal force is determined by three factors. The mass of the object, because that determines how deep the mass tries to sink into the surface, presses down on the surface. The gravitational field strength is just G, so M, lowercase m, G. G is 9.8 on our planet Earth, we all know that, but if you move to a different planet, then G can either be higher or lower. So the gravitational field strength, G, 9.8 on Earth, that has an effect on the normal force, because remember, if you calculate the weight of an object, W, in grade 9 we learned that gravitational force or weight is equal to the mass times G. So obviously the weight of an object will have an influence, an effect on how hard the surface must push back to prevent that object from falling into the surface. And then the third factor is not always present, but in grade 11 we definitely work with diagonal forces. So when you have any diagonal push or pull forces, that will also influence your normal force. So when you have to calculate or draw your normal force, especially calculate, remember you need to always take into account those first two bullets, the mass and the G, the gravitational acceleration of the planet. And then the third bullet, when there's a diagonal push or pull force, then that will definitely have an influence on the magnitude of your normal force. And then the last bullet is also very important, because sometimes students can just overcomplicate a question. Guys, the normal force is independent of whether this object is stationary, moving at a constant speed, or accelerating. Did you all hear me? There's only three factors influencing the normal force is the mass, G, and then if there's any diagonal forces or components present, then that will also have an influence on the normal force. But that last bullet, guys, whether the object is stationary, moving, constant speed, or accelerating, that will not influence your calculation of your normal force. So please don't overcomplicate and try and figure out whether there's a difference between these type of motions. No, there's not. Okay, the normal force is always the same regardless of the horizontal motion of the object. So in this video, we will look at 6 different scenarios that your normal force differ from each scenario, and we will draw the force diagram for that scenario and then use the force diagram to formulate an equation, a formula that you can use to calculate the normal force for that scenario. Guys, now you can figure this out on your own every time that you write a test or an exam, but why would you like to waste time by figuring out things if you can watch this video now, understand where we got the formula for normal force, and then just memorize it? It's just a waste of time to reinvent the wheel, to reinvent and find the normal force every time, in every situation, in every test or paper. So please, I urge you, memorize the normal forces for each of these 6 different scenarios. Now, the first scenario is when an object is on a horizontal force and there's either no force acting on the box or the object. So on the screen you see a 30 kilogram box, or there is a horizontal force. Now remember, we can have a diagonal force or an upward force or a whatever force, but this scenario is for a horizontal surface and either no forces or only horizontal forces. So let's say there you have your horizontal force. If we then draw the force diagram, we will have that force to the left. We will have gravitational force always present on any planet. And then, because the object is on a surface, this object will experience a normal force. Because you can see that objects lying on a table or on a floor does not sink into, these objects do not sink into the floor or the table. They stay on the surface. Why? Because of the normal force. Because the job of a normal force is to prevent an object from falling or moving into the surface. So there's definitely a normal force on that table. Moving on, very, very importantly, that object is not hovering above the table. It's not sinking into the table a little bit. It is right on the dot on that surface. That means that your normal force is equal in magnitude but opposite in direction to each other. Why? Because in grade 9 we learned about balanced forces, and we know that if an object is stationary like this box, then we know that all the forces up cancels out all the forces down, and that is why this object stays on that horizontal surface. Yes, it can move horizontally, but it will not move vertically. And because it's not moving vertically, you know that the normal force and the gravitational force is equal in magnitude, opposite in direction, and that is why these two forces are called balanced forces. So not all the forces are balanced, because remember, you still have this force F. I'm talking about these two vertical forces. Fg balances the normal force, and that is why your object stays on the surface, not hovering above, not falling down. And remember, this is for any objects, whether they are stationary, moving at a constant speed, or accelerating. Now, if we take the free body diagram and then try and formulate a formula for the normal force, then it will be very easy. The normal force is equal in magnitude to the gravitational force, which is just the mass times g, which is 9.8 on our planet. So remember, little g is the gravitational field strength or the gravitational acceleration on a planet. All right, so very easy peasy. Objects on a horizontal surface, whether they are stationary, moving at a constant speed, or accelerating. Let's quickly look at an example. We have a 2,000 kilogram bus, and now the examiner can tell you this bus is either stationary, it's moving at a constant velocity, it's accelerating west. It doesn't matter, because as long as that object is not hovering above the road or sinking into the road, then we know that the normal force is equal to the gravitational force. And we can start our calculation by doing just that. So the normal force, mass times g, so you can see I've substituted the mass, g, and there, ta-da, there's my normal force. The normal force, the direction of the normal force, you can either write like I did there, 0 degrees, because remember that's 0, 90, and so forth, going clockwise, or you can just say upwards. It's totally acceptable just to say upwards. That's also correct. The next scenario is the object is still on a horizontal surface, but now you have a diagonal push force. So remember, on that first slide, one of the first slides, we said that the three factors determining your normal force is mass, g, a gravitational field strength, and then if there's any diagonal forces with the components, perpendicular components, then that will have an influence on the normal force. So we need to look at examples like this. So this is our second scenario. So step one, let's draw a force diagram. Before we draw the force diagram, please remember that any diagonal force can always be resolved into its perpendicular components. And remember what I said on the video of perpendicular components. Perpendicular components represents the effects that the force have. And then on this, on your screen, you will see Fy pushing down. And you must immediately think that this is important, because if there's a downward component on this box, then the surface must work harder to prevent that object from sinking into the surface. So my normal force will now increase because there's this extra pushing down effect of your diagonal force. So let's draw our force diagram. We start off with the two forces that we know that will be there. That will be your gravitational force and your normal force. Then we add that diagonal force going out from the dot. And let's add the two components. Now, because this box does not sink into the table, we know that all the forces upwards is equal to all the forces downwards. Otherwise, that box will either have hovered around the table or it would have sinked into the table, but it's not. So we know that all the forces up is equal to all the forces down. And that is why I have drawn these specific lengths for the vectors. Very difficult word for me to pronounce. Anyway, that is why you can see that Fn is a little bit longer than Fg and Fy individually. But remember, Fn must be equal to Fg plus Fy, and that is why the length of F1 must be equal to the length of Fg plus Fy. Why? Because all the forces up must cancel out all the forces down in order for that object to stay on the surface. And from this, we get this equation for the normal force. So when you have a diagonal push force, then please learn that the normal force is then equal to the gravitational force plus this extra y component pushing down and adding that extra weight, you can maybe call it in inverted commas, on the surface. And that is why your normal force must work harder, because this y component was added. Now, if you look at this equation, you can maybe extend it a little bit more by saying that Fn, let me just get a white pen. Fn, you can maybe say something like, so therefore Fn is mg, because remember, gravitational force is equal to Fg, and then your y component, guys, is here. So if that force, where will my theta be? If that is theta, then Fy will be F sine theta. Okay, but that is only for this triangle, okay? All right, or that triangle. Yeah, that triangle. So please, oh yeah, that's another thing, guys. Sometimes we write a test or an exam and then people say that Fy will always be F sine theta and Fx is always F cos theta. Guys, that's not always true. It depends on which it really depends on which triangle you use, either this one or this one. So please do the trigonometry and don't learn silly rules. That's not always true. Please, if you learn a rule, make sure the math is correct. Okay. So let's quickly look at an example. We've got Zara pushing an 8-kilogram trolley with a 20 Newton force. So there's the force at an angle of 40 degrees relative to the horizon. So the trolley is on a surface, on a planet, so we have gravitational force, we have normal force, and then we have that downward diagonal pushing force. Because it's a diagonal force, I know that there will be a x component, and remember the effect of the x component, or the x component represents the forward motion effect of the trolley. And again, we have this downwards component pushing the trolley deeper into the surface. So if they ask you to calculate the normal force, you just write down your formula that you've learned and memorized, okay? And then for the gravitational force, you can just say 8 times 9.8. And then for Fy, where did we get the y component? We got it in this triangle. If you look at that triangle, then Fy is opposite from 40 And that is why we represented the y component with 20 sine 40. And then my magnitude, 91.26 Newton, upwards, or you can say 0 degrees. The next scenario, and this is our last scenario on a horizontal surface, is when you have a diagonal pull force. So let's first start with drawing a force diagram. Remember that any diagonal force can be resolved into the two components. And if we look at the two components, we can see, or we know that the x component will have the effect of pulling this box to the left. Okay, so if x is usually responsible for the horizontal motion. And then you'll see Fy, but this time Fy is upwards. So Fy will pull the object a little bit up from the surface. And this must tell you that the normal force will now be a little bit smaller. Why? Because of this extra upwards lifting effect that Fy has on the box. So Fy will lift the box. The downward pressing weight force of the box on the table will not be as big, and therefore the surface does not have to work as hard to prevent the box from sinking into the surface. So I predict that the normal force will be smaller this time. So if I draw my force diagram, I have normal force, gravitational force, and then I have that diagonal pull force with the two components. Now again, this object is not sinking into the surface, it's not hovering above the surface, and remember, this is regardless whether the object is stationary, moving at a constant speed or acceleration, it doesn't matter. But if that object glides or stay on that surface, we know that that means all the forces up cancels out all the forces down. The vertical forces are balanced. They are cancelling each other out. They are equal in magnitude, opposite in direction. Again, let's talk about the length of each vector. Fg is this time longer. Why? Because remember, for that box to stay on the surface, Fg must cancel out Fy plus Fn. So the combined length of Fy plus Fn must be equal to the length of Fg. So that is why Fg is longer than Fn, because Fn plus the y component must have the same combined length as Fg. Now, if you look at your force diagram and we try to formulate an equation or a formula that you can use to calculate Fn with, we see that the forces up is Fy plus Fn is equal to the force down, Fg. Now, if you want to get Fn alone, remember we are trying to find an equation for the normal force. So we want Fn alone. That means that we need to take Fy to this side. So Fy will become minus Fy. And remember I said that I predict that the normal force will be a little bit smaller. And that is why. Your normal force will be less than just the weight of the object. Why? Because of this little bit of help of that diagonal force where Fy represents the effect of lifting the box a little bit from the surface and making it easier for the normal force to prevent the box from falling into the table. If we're looking at an example, I've got a tractor pulling a 200 kilogram trailer with a 1000 Newton force at an angle of, okay, so there's your force and the angle will be then there. So first of all, we always draw a force diagram. You must always draw a force diagram. And remember, when you draw your force diagram, Fg, the length of Fg must be equal to the combined length of Fy plus Fn. Then we write our formula for Fn, which we memorized. and then Bob's your ankle, ankle, you choose. Bob's your uncle, and then you just substitute because you've memorized it. It's easy. Just again, where do you find Fy? Remember, Fy we will find from your free body diagram. And it's your choice, guys, whether you choose to work in this triangle or whether you choose to work in that triangle. It is up to you. This is trigonometry, guys. So please make sure that your math, that your trigonometry is fine. And then you just punch the numbers into your calculator and there's your answer. And again, the direction of the normal force is 0 or just upwards. So our second type of scenario is when we have the objects on an inclined plane. So on the screen, you'll see our good friend, the 30-kilogram box, being just sitting there on a slope with an angle of theta. So theta can be anything between 0 and 90. Now, the first type of forces that we will look at is if we have no applied forces and we only have parallel forces acting on the box. If there's any applied forces, those forces will be parallel to the surface. Now, if there's no other applied forces and the box is just sitting there, we know that gravitational force is definitely acting in on the box, and then of course your normal force. And remember to always draw your normal force perpendicular to the surface. Now, if I add my FG components, my parallel and my perpendicular components of the gravitational force, and if I pretend to be an observer here on the surface, and I look at the force diagram like from that side, parallel to the surface, then the normal force will be in line with F parallel. And because the box is not hovering above the surface, it is on the surface. Whether it's moving at a constant speed, whether it's accelerating on the surface, it is sliding on the surface. It's not hovering above, it's not sinking into the surface. So then we know that the normal force must be equal to F perpendicular in magnitude, but opposite in direction. So from this simple diagram, we can see that the normal force will be equal to the perpendicular component of the gravitational force. And remember, that is only in magnitude, but opposite in direction. Now, if we add an applied force, it doesn't get much different, and that is why I'm discussing those two different scenarios on one slide. Because even if you add an applied force, and your force diagram looks like this, and I'm just going to draw this. So let me just draw this yellow line. So I always just draw like a thin pencil line as a reference, just to show myself where the surface is. So there's the surface. My normal force is perpendicular to the surface. And if I add the two components of the gravitational force, then it is clear, just as with the previous example, that for this box to stay on the surface, it means that the normal force must be equal in magnitude than F perpendicular. Opposite in direction, but equal in magnitude. Why? Because those two forces, or the one is a force, the other one is a component, need to cancel each other out in order for the box to stay on the surface. So it doesn't matter whether you have no applied forces or if you have applied forces. If those applied forces are parallel with the surface, so if you look here on the left-hand side of the screen, parallel means it must be in line with the surface. So as long as you have any applied forces like that or no other applied forces, then your normal force will be equal to the perpendicular component of gravity, gravitational force. And we know that from our previous work that F perpendicular is equal to mg cos theta. It's the weight times cos the theta of the slope. So here is an example of what we've just discussed on the previous slide. A man pushes a 200 kilogram crate with 100 Newton force parallel to the surface. So there's your applied force, and that is definitely parallel to the surface. Calculate the normal force if the slope is angled at 20 degrees. So that angle is 20 degrees. Our first step is always to draw a free body diagram. So again, let me just draw my thin yellow line indicating the surface, because then I have a better understanding of what's going on. So Fn is perpendicular to the surface, and then you have that F applied force parallel to the surface. Now, if I add the two perpendicular components of gravitational force, I again have the same scenario where you have that the normal force must be equal in magnitude to F perpendicular. Otherwise, this box would not have stayed on the surface. So these two forces need to cancel each other out. So the one is a force, the other one is a component. But these two vectors need to cancel each other out in order for that crate to stay on the surface. So even if it's moving, remember, whether it's stationary, moving at a constant speed, or accelerating, as long as that crate stays on the surface, these two vectors must be balanced in order for that crate to stay in that specific position. So if you write that down, it means that your normal force is equal to F perpendicular, which we know is equal to mg cos theta. Remember that mg is also just the weight or the gravitational force acting on the crate. And then you just substitute all your values. The mass of the crate is 200. Remember, the slope is 20 degrees. And there you go. There's your answer. Just look at the direction of the normal force on a slope. So on a slope, you can't just say upwards, because upwards means this, and the normal force, if you look at your free body diagram, is definitely not just upwards. So you have to say perpendicular to the surface up, or you can say away from the surface perpendicular. You have to use the word perpendicular. So if you want to say away from the surface, you have to say perpendicular away from the surface. Right, second scenario on an inclined plane is when you have a diagonal push force. So remember the previous example, we had a applied force which was parallel to the surface. But now we have a yellow applied force, and it's not parallel to the surface. If you pretend to be a mad scientist and you stand on that surface next to the box, then from that person's view, this force is then a diagonal push force. Remember that when an object is on an inclined plane, you need to imagine standing on that surface, on the inclined plane. And for anybody standing on that inclined plane, then this force will definitely be a diagonal force acting on the box. And remember, all diagonal forces can be resolved into their perpendicular components. So even this yellow diagonal force, remember, relative to the surface, that yellow force is a diagonal push force. So turn your head a little bit, turn your head, and then look at the force, and then you'll see the force is diagonal, and it has an Fx and Fy component. And this Fx component, this is now parallel to the surface. And Fy is perpendicular to the surface. If you draw your free body diagram, there's your usual suspects, the normal force. So let me just draw my surface. Okay, let me just make a thin line. There's my surface. Okay, normal force perpendicular to the surface, gravitational force straight down, and then I have the two components of the gravitational force. Now, if you have to add that yellow applied force, it will be somewhere there. But remember, it also has two perpendicular components. And as I previously said, Fx is always then parallel to the surface of the slope, and Fy will be perpendicular. So if that is my slope, you can see that Fx is parallel as well as F parallel, and Fy is perpendicular to your surface. So that is how you draw the free body diagram for this scenario. Again, if that box stays on the surface, whether it's moving with a constant speed, acceleration, or just standing there doing nothing as usual, then we know that the normal force must be cancelled out by something down here. And this something down here we must find on your free body diagram. So in this case, we have another component perpendicularly down from the surface. So remember on the previous slides, Fn was equal to F perpendicular, because F perpendicular was the only force component down here. But now we have another one. We have Fy of the yellow applied force. So this can't be true anymore. You need to add that yellow component as well. So in total, always remember, if that is your surface, then all the forces up from the surface must be equal to all the forces down from the surface in order for that crate to stay on the surface. So we'll write it like this. All the forces up is equal to all the forces or components down. And that is how I got to this equation. And then just remember, F perpendicular, how do you get F perpendicular? That is just equal to mg cos theta, or your weight times cos theta. And then where will you get Fy? Where will you get the y component of this yellow force? Well, you have to work in that triangle, or whichever triangle you want to work in, but you will find Fy doing a little bit of trigonometry there. Let's look at a question. We have a man doing all the work as usual, and this guy is pushing a 20-kilogram trolley with 100 Newton force, so it is a diagonal push force. If you stand here on the surface with this very handsome guy and you look in his direction, then this applied force will definitely look like a diagonal push force. All right, very important, there are two angles here in this scenario. Don't get confused. You've got the 20-degree angle with the slope, and then you've got this angle there. So your applied force is diagonal relative to the surface, so that force there is 30 degrees. So make sure that you see that these two angles are not the same. You have the angle of the applied force there, okay, relative to the surface. What is that angle? That is 30. But then you also have a second angle there, and that is the angle of the slope. Now we know that if we have this scenario and we have to draw the force diagram, then again, let me just add my surface. Okay, so there's my surface. My normal force is perpendicular to the surface, and I have my gravitational force. But let's add the yellow push force of this guy on the trolley. So there is my yellow push force, and remember, this is the surface, guys. So F parallel is parallel to the surface, but also the X component. So this, let me use here. So this yellow force, remember, has an X component and it has a Y component. And that is what you see here. So if you have to calculate the normal force, we've seen on the previous slide, and you need to learn this, that if you have a diagonal push force on an inclined plane, the equation, the formula that will help you to find the normal force is this. F perpendicular plus the Y component of that yellow force. So this is my substitution. So F perpendicular is mg cos 20. Why 20? Because remember, if you calculate F perpendicular, it's mg cos theta, and then this theta is the angle of the slope. But when you are dealing with Fy, which is this one, Fy is relative to F, which is at an angle 30 degrees to the surface of the slope. So that is why this angle is 30, but this angle is 20. And then I just substitute all my numerical values and I get my value for the normal force perpendicular to the surface up, or you can say perpendicular away from the surface, but you have to say perpendicular. You can't just say away from the surface, guys, because away from the surface can be this or it can be this. That is not perpendicular to the surface. Last scenario, so last type of normal force that you get is when you have a diagonal pull force on an inclined plane. So again, let's bring in our mad scientist, which will be parallel to the surface. So this person stands on the surface and looks parallel at this applied force. And for that person, so tilt your head, guys, tilt your head and look at that yellow force with a tilted head as if you are standing on that surface. And then you will see that that yellow force is actually a diagonal pull force relative to the surface on which the slope is. That force is not parallel to the surface. That's very clear. So then it must be a diagonal force relative to the surface. So again, I can resolve that diagonal force relative to the surface into its two components. And when I draw the force diagram, I always start off with my usual suspects, the normal force, the gravitational force. There's my surface, so normal force is perpendicular. And if I then add this yellow applied force, it will be up. So there, remember, the blue line is your surface. So that yellow diagonal force relative to the surface diagonal, that will then be like a kind of upwards pulling force, pulling the crate somewhere to the right, little bit upwards from the surface. So that yellow applied force also has two perpendicular components, the Fy and the Fx. So again, because this box stays on the surface, whether it's accelerating, moving at a constant speed, or just being stationary, then we know that all the forces up away from this surface must be equal in magnitude to all the forces or components down. So all the forces up is equal to all the forces down in magnitude, but opposite in direction. And that is why these forces and components can cancel each other out, and that is why the crate or the box stays on the surface. Now, if we write that, it means all the forces up, which is normal force, plus Fy is equal to all the forces down, which will be F perpendicular. Now, remember, in this chapter, we are trying to solve or get create formula to calculate F normal. So let's try and get F normal alone. That means that you need to take the Fy, the yellow Y component of your diagonal force, to the other side. So that means that it will become F perpendicular minus Fy. And that is exactly what your formula for the normal force is when you have a diagonal pull force on an inclined plane. That is how you will calculate the normal force. Now again, as with the previous slide, you need to be careful about the angles. Let me do it like this. Let's say this yellow applied force is relative to the surface at an angle of 20 degrees. So that angle there is 20 degrees. Okay, but the angle of the slope, this angle there, is 40 degrees. How will that, or how will we substitute those two different angles into our formula? Okay, let's try. So you will write Fn equals, now F perpendicular is mg cos theta, okay? But remember, F perpendicular is relative to the surface. So that theta there, that is where you will substitute the 40. And then you will have minus Fy. Now Fy is here. Sorry, Fy is there. So Fy is next to that angle. And if this angle is 20, so let's go back here. If this angle is 20, then that angle is 70. So your Fy here, let's just clean everything here. Let's not confuse ourselves. Okay, so that angle is 20, that angle is 20, so that angle is 70. So if you want to write an expression for Fy, then it will be either F cos 70, or you can call it F sine 20, whichever you prefer. All right, so this is very important, that you'll see that when you have a diagonal pull or push force on an inclined slope, that you need to be careful about those two different angles on your sketch. Now guys, these last two examples are level 3 or level 4 questions. They're not asked regularly, so it's not like a regular question. This is more challenging, and we don't always ask these pull or diagonal push force on an inclined plane. But if we look for a level 3 or a level 4 question, then this is what it will be.